So in this video, we will go over some applications of the Newton's method, and that will also be part of the first homework assignment for you all. All right, so the first application, a very well-known problem, find an approximate value for square root of 2. So find an approximate value for root 2. Well, when I say that, let's be more precise, and I want to be an approximate value for root 2 up to 9 decimal places. 9 decimal places of accuracy. So it's really not an when I say approximation, I mean I want to have a certain sense of accuracy as well. Accuracy. And these decimal places will tell me exactly how accurate I want to be. All right, so by just looking at this, you might be surprised to see what does Newton's method has to do with that. Remember, after all, Newton's method is just to find the roots of a polynomial function, or the roots of any function for that matter. If it's polynomial, it's easier to take the derivative, and so as a result, life is much easier. But how about the root 2? So the key idea here is to find a polynomial, a function, f of x, whose root will be square root 2. So this part is a little bit requires some creativity. So which polynomial has as a root square root of 2? Well, it's easy to do it actually in the following sense. So we need to find the actual function, but what we can do is the following. By just labeling this as x, so or let's be more precise, x is equal to square root 2. What we can do is we can clearly take the square of both sides, implying x squared is equal to 2, and finally moving that 2 to the left hand side will give us x squared minus 2 is equal to 0. Aha! So basically the actual function that we want to find its root for is x squared minus 2. Do you guys see that? The two roots of this function are plus and minus square root 2. So as long as I'm on the positive side, I should be okay. All right, so for my initial estimate, when I apply Newton's method, I will start with an estimate which it will be positive. And in this case, probably, I mean, we can eyeball it and we can know that clearly square root 2 is squeezed somewhere between 1 and 2. So I think a good guess would be 1.5, right? So if you guys want, we can start with 1.5. But actually, anything above 0 should be just fine, right? So 1.5 will be my initial estimate. x0 equals 1.5. So starting with that, I should be able to generate the whole sequence of terms after each iteration. But first, let's write out the equation again. X sub by Newton's method, we know that x sub n plus 1 is simply x sub n minus f of x sub n divided by f prime of x sub n. If you remember my first video, or the second video on the Excel application, we gave the formula in the wrong way. So it was f prime over f. That's not correct. The correct version is this one, f over f prime, right? Awesome. So let's first, I think I will need the derivative. So as a result, let me just go ahead and calculate the derivative of the function f, which turns out to be pretty simple. It will be just 2x. So if I were to substitute in our recursion now will look like this. X sub n minus x squared minus 2x sub n, that's also a sub n, divided by substitute x sub n into the f prime function, namely this one. 2x sub n, right? And all I now need is to find the common denominator maybe, and then to simplify the expression. Let me just go ahead and do that to see if I can find a simpler expression. Otherwise, we can just go ahead and even start out from here, right? So if you don't want to do it, and ultimately I would assume that you guys will probably use Excel anyway, so there's no need for that. Okay, good. So now we can go ahead and start iterating this, starting with our initial guess of x0 equals 1.5. Let's plug in the values and let's see what will be the subsequent values that will come out of it. So as a result, so therefore, starting with x0 equals 1.5. So let's start with 1. X sub 1 is equal to x sub 0. So when I say x sub 1, what I'm doing is in that formula here, I'm just substituting n equals 0, right? When I actually, let me be more specific then, right? So I don't want to create any confusion or whatsoever, right? So for n is equal to 0, as a result, the formula becomes x sub 0 plus 1, which is x sub 1, right? So x sub 1 is equal to, so plug in n equals 0 again, so that's x sub 0 minus x sub 0 square minus 2x sub 0, all divided by, actually no, the function is just x squared minus 2, again another silly mistake, so this is just a minus 2, not minus 2x sub n, just minus 2. All right, so let me be clear there. So minus 2. There you go. But the denominator is the derivative, and the derivative is clearly 2x. So when I substitute x sub n into 2x, I get 2x sub n. There you go. All right, so divided by 2x sub 0. Here you go. So when I plug in this value of 1.5 minus 1.5 square minus 2 times 1.5, all divided by 2 times, sorry, again the same mistake, right? Why do I keep doing the same mistake? There you go, just minus 2. Okay, just minus 2 divided by 2 times, 2 times what? 1.5, right? So let me just write it like this, 2 times 1.5, and from there, if you have a calculator, we can easily get that x1, or let's do it in 2 steps, let's calculate it together. 1.5 minus 1.5 squared is 2.25 minus 2, that will give us a 0.25 in the numerator, and in the denominator we'll have a 3. So now I think it's a good place to just stop and use a calculator to derive the desired result. So we have 0.25 divided by 3 equals plus minus plus 1.5. I got a 1.417. Or if you want more, actually, because the question says 9 decimal place of accuracy, so let's go all the way. 1.41666666. Ultimately, I want to add a 7 in the answer. 1, 2, 3, 4, 5, 6, 7, 8. And then the last one will be a 7. There you go. All right, so that's x sub 1. I probably want to go a little bit further than that until I keep getting the same results. So, right, so let's just keep doing it. And by the way, you can easily check with a calculator what is a square root 2, right? On a calculator, I have a calculator in front of me right now. Actually, I have my iPhone, so let's just go ahead and do that. So if I take the square root of 2, my calculator tells me that the actual answer to this problem is supposed to be, so let me just write it here. Calculator says that root 2 is equal to 1.11421 3562 356 1 2 3 4 5 6 7 8, one more, and then a 2. Let's see if I can get to the same answer and how long it will take me to get to that answer. All right, so let's continue with x sub 2 then. But by now, we are pretty confident. We know exactly what's going on, right? So let's continue with the same color, I guess. So x sub 2 is equal to, just plug in that value. And, well, that's pretty ugly. So I'll just write it like this, minus 2 divided by 2 times x sub 1. All I will do is over here, actually, let me just highlight it instead. It will be even easier. There you go. So over here, here, and here, in this expression, if I were to substitute this, then what would come out at the end of this step would have been 1 point. Okay, check this out. So I did it earlier. So 1 point, and please do so and substitute these values. See if you can get the same answer to 15686. 15686. That's pretty good. So that's 9 decimal place. Let's check x sub 3. It's still a little bit off, right? So far the agreement is 414 after the decimal place. 414213. Here it is 41421. Okay, so we still have some error over there. So we need to go one step further. The 5686, the last 4 digits don't match. Here we have 3562, right? A little bit more, so probably one step further and we will be pretty much done. So if you check the next term, so it will be just substituting, so this expression minus 2 over 2x2, and that will give us, if you were to now substitute let me color code it again. So if you were to substitute this expression onto here, here, and here, then what you would get would have been the following long expression, but I think it does the trick actually. 1.4142, 1.4142, 13562, 13562. Now let's compare them and look at that. 3562, 3562. Wow. So this is already 9 decimal places of accuracy. Very, very good. So you might say, wait a second. So we were able to get that 9 decimal places of accuracy simply because what? We started at a good guess. That's true. We started because we knew that from the beginning square root 2 sounded like it, because it is between 1 and 2, we kind of guessed that 1.5 is a good place to start. But even if you didn't start at a close point like this, suppose that instead you started at 1 billion. So ultimately you will find the answer, but it will probably take you, instead of taking you 3 steps like in our Excel video, I think it will probably take you 10, 20 or 30 steps. But ultimately, because in Excel it's just like, it will take you just 1 or 2 minutes to program it, so life should be pretty good as well. All right, so this was our first example. A second application will be the following. So yes, let me give you an example of a trigonometric function next, and then maybe an example of a logarithmic function, and then I want to, in the end, ultimately finish with an example where Newton's method failed. So you need to be also aware of some pathological situations where there are functions which are not well behaving, and as a result, the derivative will blow off, and so it won't work. So, but first let's have a look at this. The question is the following problem. Our second problem, or example, maybe I should call it example 2 instead. Example 2. So the question then is that we want to solve the following equation. So solve the following in real numbers, obviously. X is equal to 1/2 of cosine x. All right, so just to remind you, so it might be a good idea to draw the graph. If you guys remember the cosine function, let me just do pi, 2 pi, and maybe minus pi on this side, and so on, minus 2 pi. So the cosine function happens to be always squeezed between -1 and 1, so +1 here, -1 here, and it takes the value of 1 at 0. So that's the nature of the cosine function. And if you remember from your pre-calculus classes, cosine pi over 2 is 0. And cosine pi is -1. Cosine 3 pi over 2 is back to 0. And cosine 2 pi is 1 again. So it's a periodic function like that. So it will be 0 here, -1 here, 0 here, 1 here. So therefore, cosine will be on the negative side. It will look like this. It's like the sine function, except that it is shifted by pi over 2, right? So it's a function like this. Now, this is the cosine function. So if you want, what I can do is I can move that 1/2 to the left-hand side. So the equation turns out to be solving this instead, cosine x. Does that make sense? So instead of solving x equals 1/2 cosine x, I'm going to solve 2x equals cosine x, which is the same thing. So what I want is to intersect this with 2x. So 2x, let's have 2x with a different color, maybe green color. So 2x is a function which goes through the origin, and it has a slope of 2. Remember that pi is 3, oops, sorry for that. Pi is 3.14. So pi over 2 would be 1.57, I guess. So because our function is 2x, so it will hit the value 1, y equals 2x, will hit the value 1 at 1/2, right? So maybe very close here. So there you go. So it's a steep function because it has a slope 2. There you go. So it is this function. And the question is, they will just intersect at one point. That's what the question is asking. What is this value? By just eyeballing it, I can see that it will be less than half, between 0 and 1/2, basically, right? And that's what we want to compute. And let's see if we can find that. So eyeballing this solution should be should be a little bit less than, a little less than 0.5, basically. But even if we didn't know that, even if I didn't draw this sketch, I should still, using Newton method, I should be able to still solve it. The benefit of drawing the sketch is if somehow, for some reason, Newton method does not give you a convergent answer, if each subsequent iteration of the xi sequence, if it starts diverging, looking back at the function is an important thing. So being able to draw the function, right? But otherwise, if the function is well-behaving, smooth function, you should be fine. All right, so let's now go ahead and solve this problem, I guess. So very easy, straightforward. We will use the same trick that we did in the previous question. Move that cosine x to the left-hand side. So the question is basically asking you to solve this, which you can reinterpret as finding the roots of this function. Does that make sense? So find roots. That's it. And when I say roots, I know that there will be only a single root by demonstration, by inspection of the graphs of these two functions. So it is very common sense. So the actual recursion is this. By Newton method, we know that the recursion will look like this: x sub n minus f of x sub n divided by f prime of x sub n. So x sub n minus, so plug in x sub n into the function, so which is a very straightforward matter. There you go. Divided by, now I need to take the derivative, and in the derivative plug in the value. So the derivative of 2x is just a 2. The derivative of cosine of x is minus sine of x. So that will end up being plus sine. And then now I can plug in x sub n. There you go. And now we can go back to action. Because I know the answer will be extremely close to 1.5, I might as well just start... sorry, 1/2 I should say. Because the answer will be close to 1/2. If you guys want, we can start directly from 1/2 and I don't have to do too many calculations. But even if you started at a 2, a 3, a 5, whatever, you should have gotten the same answer as well, right? All right, so let's now go ahead and... Did you see how we were able to translate this equation, solving an equation, into this problem, finding the roots of this? So these two problems are equivalent problems, right? Let me highlight them. Solving this and finding the roots of this thing are the same things, and that's the trick. So sometimes it's not direct, like in the previous question, all right? So for instance, evaluating root 2 up to 9 decimal places of accuracy, only after you figure that it is the same thing as finding the roots of this function, that's when you realize, I can use Newton's method. The next step is always to find a guess about the starting point. If you have good drawing skills, like you can imagine how the function looks like, it will be easier for you. In that case, you will approximate to the correct answer faster. But even if that's not the case, you should still be able to do it, though maybe it will take a little bit longer. Sometimes, though, a Newton method will fail. And I'll give you an example of where it fails. And so this is when the picture turns out to be important. So if there are some certain ranges of guesses where it will fail, then you want to be able to start from the correct range before you implement the algorithm, basically. All right, so having said that, again, let's go back to business. Now we can go ahead and calculate x1. So x1 is just substituting n equals 0 here. So and I'm making the calculation. So x1 will come out as x0 minus 2x0 minus cosine of x0, all divided by 2 plus sine of x0. Remember that x0 we picked it as 0.5. Maybe I should have said that earlier, where we pick x sub 0 equals 1/2, basically, or 0.5. All right, so we have 1/2 minus 2 times 1/2 minus cosine of 1/2, this is in radian, divided by 2 plus sine of 1/2. And if you just plug into any calculator, scientific calculator, I should say, x1 comes out as what? As 0.45063. 0.45063. So, of course, I don't have a sense of how close I am. Let me just do a couple more, maybe 2 more evaluations, and then let's see if we're approximating. x2 will be just x1 minus 2x1 minus cosine of x1 divided by 2 plus sine sine of x1 equals, so plug in, substitute x1 with this monster expression, 0.63, this is pretty weird expression, 0.45063 minus cosine of 0.45063, oh gosh, handwriting not good, and then divided everything by 2 plus sine of 0.45063, and that's it. When you plug in everything into your calculator, long and behold, x2 comes out as 0.450, I think 18. So far we are converging hopefully to an answer, so which is the good news. At least there is an answer after all. We want to see how close we will get. Suppose that the question is asking up to 5 decimal places of accuracy. So let's see if we will make any improvement after here. So x3 in a similar way, you just substitute this expression. Okay, let's just directly substitute into the same thing. So 0.45018 minus open 2 times 0.45018 minus cosine of 0.45018, all divided by 2 plus sine of 0.45018, and long and behold, if you make the calculation up to 5 decimal places of accuracy, guess what? 0.45018. Nothing changes. Yay! We already approximated to an answer. Obviously, these two numbers are probably different on the 6th, 7th, or 8th decimal place, but that's it. So up to 5 decimal place, I can stop here, right? So this is the place where I can stop the algorithm. So stop algorithm, simply because it doesn't improve any further, because x2 and x3 are equal, so no need to calculate x4. x4 will obviously be the same as x3 because we will resubstitute the same expression into our formula, so we won't gain anything. And the answer is 0.45018. That's it. So this is the value for which well, it's basically the solution to this problem, basically. And quickly, you can use a website like Wolfram Alpha to establish that as well. Awesome. So if you guys are not very tired, let's have a look at a third example, and hopefully we can just wrap up with that, and maybe I can have another video for the cases where Newton's method do not converge after all, and how to remedy the situation. So in this example, we are going to look at, well, actually, we're going to solve this. Okay, let's try to solve the following equation. 3 times sine of x, oops, come on. 3 times sine of x is equal to, let's say, the natural logarithm of x. So this is the natural logarithm function. It's a logarithm where the base of the logarithm is e, the Euler number, which is 2.713. Okay, so, well, the question is, solve this. It turns out, if you were to draw a picture, and this time I'll be careful here again. So we have a 3 here, minus 3. So that's the range for the left-hand side. Remember that sine x is always between minus 1 and 1. Let me make note of that. Remember, the sine of an angle, sine of x, is always in the range of minus 1 and 1. And because we have 3 sine of x, we need to stretch it by a factor of 3, so that's why the sine will be stretched like that. And all I need is, again, to find out the the period. Again, the period here is 2 pi, right? So 2 pi, and so maybe I need to mark pi here, pi over 2, 3 pi over 2 here, and so on, just like I did in the previous question, right? So maybe 4 pi, 3 pi, and then 5 pi over 2, and then 7 pi over 2, maybe somewhere here. All right, so sine will be, again, a periodic function. Sine 0 is 0, sine pi is 0, sine 2 pi is 0, and so on. Sine 3 pi, 4 pi. And the sine function, and then similarly for the negative side, sine minus pi, sine minus 2 pi, and so on. So our function will look like this. At pi over 2, it will hit the value 1. At 3 pi over 2, sine 3 pi over 2 is minus 1. At 5 pi over 2, it's plus 1. 7 pi over 2, it's minus 1, and so on. So and the same thing on the negative side as well. Just put, okay, mark some marks there. So on the negative side, it will be, there you go. And on the positive side, it will look like this. So that's our sine function. Now we are, or 3 sine of x function. So this red is y equals 3 sine of x. Now we need another function. On the right hand side we have the ln function. Now the natural logarithm function, when you evaluate it at 4 different values, for instance, in our case, so this is 3.14. Let me just remind you, 2 pi is 6.28. Let me just find different values for the ln function, especially for small values. For instance, it's clear that ln 0 is negative infinity. If you check it on your calculator, you will see that. Oops, what did I do again? All right, pretty messed up again. Okay, there you go. So ln 1, if you make the calculation, turns out to be 0. So it hits, this is the root of this function. Ln, if you calculate it at e, where e is the base of the natural logarithm, like I said, 2.713. So that would come out as a 1. That's still a little bit outside the range. I need to go a little bit further. Ln e squared by the property of ln. So that will be a 2. And finally, ln e cubed will be a 3. So what I will do is I have a financial well, actually, I have my cell phone in front of me. So I'm opening the calculator feature. Actually, the scientific, if you hold your iPhone like horizontal, it will give you a scientific calculator. So it has the e to the x function. So for instance, if e cubed is 20.08. So that's when the last time it will hit it. So it will be, is there a better way to describe it? Yeah, so, yeah, it's a little bit far, right? E cube is a big number. Okay, so maybe I can, yeah, this thing is pretty large after all. Maybe I should have done it a smaller value. But anyhow, so that's e squared is acceptable. It's 7.38. So 7.38 is over here. So probably, okay, my guess will be that the function will look like this. So obviously it has a 0 at, it has a root at, it has a root at 1, right? So so this one is 1.57. So it has a root right here at 1. At e, it will be equal to 1. So e is 2.718. So 2.718 is somewhere close here. So therefore, at 2.718, it will be equal to 1. So somewhere here. At e squared, which is 7.39. 7.39 would be, if I add 6.28 plus 6.28 plus 1.57, so that would be 7.85. So this one is 7.85. So we said that e squared is 7.38. So somewhere here we have a 2, is somewhere between them over here. So you can imagine, and it's minus infinity at 0. So our logarithm function will look like this. Oh gosh. And then it will probably go ahead and hit a few more points until it exceeds e cube. At e cube, once you reach e cube, it will exceed it and it will no longer hit anything, right? But until then, it will hit a couple of different values, actually. All right, so having said that, let's try to find some values. Actually, you know what? Let's try to evaluate just one of them. How about the smallest one? Let's find the smallest solution, this one. We realize that these two functions, the red function and the green function, remember the green function is the logarithm function. So this green function is y equals ln x. And our goal is to intersect that green function with the red function 3 sine x, right? Obviously they intersect in multiple points, maybe another point up there. Do you see that? So they're about to and then maybe another, yeah, a couple more times. But all I'm interested in is the smallest solution, smallest. Let's try to find out the smallest solution. Again, by just eyeballing it, I can see that the smallest solution is somewhere between 1.57 and 3.14 for the x value. Between 1.57 and 3.14. 3.14, come on. And this is a little bit, a number which is a little bit less than 3.14. I think 3 is a good place to guess, right? I mean, it's screaming to us that that's a good starting point. So let's just go ahead and use that. All right, so my starting point would be x0 equals 3. And I will just go ahead, like in the previous question, up to 5 decimal places of accuracy, I want to calculate that smallest solution. All right, smallest solution up to 5 decimal places of accuracy. For where, okay, so check this out. Using Newton's method, x sub n plus 1 is given by this recursive formula. So f of x divided by f sub prime of x sub n. So our function, oh wow, I didn't even bother writing the function, right? Let's first do that, I guess. Let's write it like this: f of x sub n divided by f prime of x sub n. Before I write it out here, let's first establish what do we mean by f of x. Obviously, all I will do is move that ln x to the left-hand side, and I'm finding the roots of that function. 3x minus ln x, and that's it. So that's our function. We want to set it equal to 0 and then find smallest root. Find smallest root. Which by our picture we know that that root is very close to 3.0, so a little bit less than 3.14, because at 3.14 the red function hits the x-axis, the green function is over there. But so yeah, we can see that by inspection actually. All right, so and the derivative of this function, just to review, 3x, the derivative is just 3 minus ln x, the derivative is 1 over x. There you go. All right, so therefore our recursive form will look like this. On the numerator, it will be 3x sub n minus ln x sub n, and in the denominator, it will have 3 minus 1 over x sub n. There you go. And now we can go ahead and substitute. Yay. Okay, so it will just take us a few minutes. If you have Excel, obviously, it will be even faster, and besides it will be more accurate as well. So if you plug in x0 in our formula, x0 is just 3. Let's just plug it in right away. 3 minus, open parenthesis, 3 times 3 minus ln 3, all divided by 3 minus 1 over, 1 over 3. Let me move it back. Okay, there you go. If you make that first calculation, x1 comes out approximately, so this implies x1 is approximately, up to 5 decimal place of accuracy, 2.79558. All right, let's go a few more. So we need to keep going. The algorithm will stop as soon as we have the 5 decimal places after equal for 2 consecutive values of x, right? All right, so if you, in a similar way, calculate x2 by just substituting this value into the formula again, which is pretty ugly, as you can see, 558 minus minus what, 3 times, oh gosh, 2.79, 558 minus, okay, ln 2.79, 558, all divided by 3, sorry, not 3 again, 2.79, 558 minus 1 over 2.79, 558, and long behold, x2 comes out. So this implies that x2 comes out approximately, I should say, approximately. This is the approximate sign is this one, so an wiggly equal sign. It comes out as 2.79, 225. And lastly, okay, so actually I mean, it depends on, you need to keep doing that until the last 5 digits will be exactly the same. It turns out that I did this previously, and I know that this will give us exactly the desired result. So 225 minus 3 times 2.79, 225, 225 minus ln 2.79225, all divided by 2.79225 minus 1 over 2.79225. Oh gosh. And long behold, guess what? x3 comes out approximately the same answer. Yay. Okay, so we have approximated to the desired result. So starting with x0 equals 3, in the next step we got x1 equals this. Then x2 came out this, and x3, we stopped the algorithm simply because x2 and x3 are giving us exactly the same value, right? Let me just make it smaller. Algorithm stops after 3 iterations because because x2 and x3 are exactly the same. It already converged to each other, right? So to that common value, which is approximately 2.79225. That's it. So this is the smallest intersection between the two, the x value. Yes. That's pretty much it. Okay, so let me stop with these 3 examples. I think the 3 examples were hopefully useful, and so you will be able to solve the first part of our first problem set based on these applications. Thank you.